Welcome back, everyone, to lecture 3 on machine learning methods for probabilistic graphical models. Last two lectures, or I should say more like last 3 lectures, what we covered are machine learning fundamentals. So this was a crash course in machine learning. Then we saw that we are going to look at 16 types of ML algorithms for graphical models. If you remember, we had 4 dimensions. The first dimension was the type of graphical model, either a Bayesian network or a Markov network. There was another dimension which was talking about what type of learning are you going to do, whether it's going to be Bayesian learning or maximum likelihood estimation. The third type talked about whether you are going to, what type of learning task are you going to perform in a graphical model, whether it's parameter learning or structure learning. And the final dimension was what type of data set do you have, whether it's a partially observed data set or a fully observed data set. Okay, so far we have looked at parameter learning algorithms for Bayesian networks for both fully observed data and partially observed data, under the assumption that the learning approach we are using is the maximum likelihood estimation approach. Okay. Today, what we are going to do is we are going to look at parameter learning algorithms in Bayesian networks for both the fully observed as well as the partially observed data case. Okay, but instead of using the maximum likelihood estimation approach, we are going to use an approach from Bayesian statistics. Right, so there is a field of statistics called Bayesian statistics, and there is a field of statistics called frequentist statistics. So maximum likelihood estimation methods, which look at data alone, belong to a field in statistics called the frequentist statistics. And then there is a field which competes with the frequentist idea called the Bayesian statistics field. Okay, so today we are going to look at the Bayesian approach for learning rather than the maximum likelihood estimation approach. We will also look at structure learning algorithms in Bayesian networks under the FOD as well as the POD case, and we will cover that next lecture. Okay, so most of our lecture will be focused on parameter learning in Bayesian networks using the Bayesian approach. Okay, so let me try to motivate you why we need Bayesian learning using the same example that we have used before, which is the example of a bias coin. So if you remember, we had a bias coin, and the coin can be in 2 states, either a heads or a tail. And we said that the parameter associated with the so x is a coin, right? And the parameter associated with x equals h. The probability of that is nothing but theta. And the parameter associated with x equals tail is nothing but 1 minus theta. Okay. And we said, how can we estimate the parameter of this model when we are given some experimental data? Okay, so the first experimental data will be, let's say we toss the coin 10 times and we got 6 heads. What is the value of the parameter theta using the maximum likelihood estimation approach? And our answer was nothing but theta is equal to 6 divided by 10. Okay. If we did a second set of experiments where we had, let's say, more time, and we tossed the coin 100 times instead of 10, and now we got 53 heads. And what is our estimate of theta? Theta is nothing but same thing, 53 divided by 100. And in the third case, if we had tossed the coin 1,000 times and you got 520 heads, then our theta would have been equal to 520 divided by 1,000, which is 0.52, and this is 0.53. Okay. So the next question that I'm going to ask you is, which of these answers will you believe? Will you believe the answer which is 0.6? Or will you believe the answer which is 0.2, which is based on 1,000 tosses, versus 0.6 is only based on 10 tosses? Intuitively, it is obvious that you will believe the experiment in which you have tossed the coin 1,000 times, okay? Because since there is more data, and you always believe more data rather than believing anything else, okay? However, unless you have large amount of data, right, relying on data alone can be very problematic. Yeah. So if, let's say, instead of 10 examples, if I had something like 3 examples, the best I could do is I could have something like probabilities which look like 0, right, or 1, where we got all 3 heads and or all 3 tails. So that corresponds to 0 and the other one corresponds to a 1. Or we could have a probability of 1/3, 2/3, and that's it, right? So there will be only like 4 possible answers in this case. And which of these probabilities will you believe? I cannot believe any of these probabilities, right? Because the number of times I've done the experiments is very, very small, okay? Therefore, relying on data alone is not a good idea. So what we want to do in practice is we want to come up with a better strategy for learning which combines data with prior knowledge, okay? So you might have certain background knowledge or prior knowledge about the process that you're trying to model, right? Or someone might have told you that the coin that you're tossing is actually more of a fair coin as compared to a biased coin. So the probabilities are maybe close to 0.5, right? The probability of heads will be close to 0.5 as let's say, close to 0.9, for instance, okay? So in that case, when we have less data, what we should do is we should believe our prior knowledge. And as the amount of data increases, we want our learning algorithm to believe the data more and more and more, okay? So what Bayesian approach does is it's a formal strategy that implements, or I should say it's a formal approach that implements the strategy, where you believe the prior knowledge, especially when you feel strongly about it, okay, and you don't have enough data. And then you believe the data when you have large amount of data, and your prior is not that strong, let's say, or even if your prior is strong, and somehow you have, let's say, zillions and zillions of examples, in that case, you are going to believe the data, okay? So that's the strategy that we are going to pursue for this class, okay? Combine data with prior knowledge. So the Bayesian learning approach is based on Bayes' theorem, and as I said before, it belongs to this field of statistics called Bayesian statistics as opposed to the frequentist statistics. Okay? So let me try to define formally this approach for you, but just alluding to Bayes' theorem. So you're given a data set D and a parameter theta, and theta is the parameter that you want to, let's say, estimate from the data set. In the maximum likelihood estimation approach, we saw that a learning task could be defined as find a value for theta such that the likelihood of the data is maximized, okay? Another way of saying this mathematically is that I want to maximize theta, okay, such that P of D given theta is maximized, okay? So what is P of D given theta? Assuming that our examples are independent and identically distributed, the likelihood is nothing but, if you have n data points, the probability of generating each point according to the parameter theta. Okay? So I want to select theta such that that term is maximized. What the Bayesian approach does, as I said, it combines prior knowledge with data, you'll assume a prior knowledge or a prior distribution over the parameter theta. Let's call that distribution p theta. Okay. Then, given data, instead of just maximizing the likelihood, what you will do is you'll find a posterior distribution over the parameter theta by combining it with your prior distribution. Okay? Namely, what we will try to do mathematically is try to compute probability of theta, okay, given data. Okay. So the question is, how can I compute p of theta given data? Okay. So I know how to compute I'm already given p of theta, I should say, and then I know how to compute p of d given theta. Okay. How will I get p of theta given d from that? And the answer is, all you have to do is use the Bayes theorem. Okay. So by Bayes theorem, probability of theta given data is equal to probability of data given theta, which is nothing but the likelihood, times probability of theta, which is nothing but the prior, divided by the probability of generating the data, okay, which is p of d. Since the denominator is always a constant, we can safely ignore it when we are trying to estimate p of theta given data. Okay, and when we do that, it turns out that the posterior, which is probability of theta given data, is nothing but directly proportional to the likelihood times the prior. Okay, so that's what the Bayesian approach is. Instead of computing the likelihood, what you're trying to do is you're trying to compute the posterior over your parameter given the data. Okay, so you have access to the prior and you have access to the likelihood. You multiply the likelihood with the prior and you get the posterior. If you look at this Bayesian approach that I just presented, right, you can see that unlike the maximum likelihood estimation approach, where you get a value for the parameter. So if you remember in our previous case, if I had 6 heads out of 10 in my data, then I would output a value for the parameter, which was nothing but theta equals 0.6, which was my maximum likelihood estimate. Okay. In the Bayesian approach, right, and sometimes it's also called as the fully Bayesian approach, you're not getting just one parameter. Okay. The output of the Bayesian approach is a posterior distribution, which is a distribution on all values of theta. Okay. So if you assume that theta is a real number, since it's a probability in this case, right? So it lies between 0 and 1. What you're going to get as the output of the fully Bayesian approach is a probability distribution over the space between 0 and 1. Okay, so it will be a continuous probability density, which ranges from 0 to 1. We can also consider a so-called maximum posteriori estimate of the posterior distribution. And what this approach does is it's similar to the MLA approach in the sense that it also outputs a value rather than outputting a full probability distribution over the parameter theta. Okay, and the way it's defined is very intuitive. What you have to do is you have to find a value for theta such that the posterior is maximized. Okay, so in the MLE, we maximize the likelihood, and in the map estimate, what we are trying to do is we are trying to maximize the posterior. Okay, mathematically, it could be stated as maximizing or finding the value of theta, right? So maximizing over theta such that p of theta given d is maximized. Okay, so one way of looking at the map estimate is that it generalizes the MLE or the maximum likelihood estimate. How? If we assume that P of theta is the uniform distribution, then since posterior is likelihood times the prior, right, and the prior is the uniform distribution, then posterior will be directly proportional to the likelihood. Since posterior is proportional to the likelihood, maximizing the posterior will be same as maximizing the likelihood. So in that case, map will equal MLE. However, if P of theta is not uniform, then what happens? Map will yield a different estimate as compared to MLE. Okay? So that's why we say that the map estimate generalizes MLE. You use P of theta as uniform, you get MLE. And if you use P of theta as any other distribution other than the uniform distribution, you get something else. Next, what we will do is we will look at an example for Bayesian learning. If you recall, right, the main aspect in Bayesian learning is that you have to specify a prior, right, and then multiply the prior with the likelihood to get a posterior. So we'll do two examples. The first example we will use discrete priors, and in the next example we are going to use continuous prior. We are going to use the same point estimation example as before, or what I mean by point estimation is that we are estimating just one parameter from data. We'll use the example of a biased coin where we have a parameter theta. And we saw that the maximum likelihood estimates when we get 6 heads out of 10 and 53 heads out of 100 and 520 heads out of 1000 were these values, right? 6 divided by 10, 0.6, 53 divided by 100, which is 0.53, and 520 divided by 1000, which is 0.52. Okay. So suppose now in the Bayesian learning context, you have a prior knowledge, and the prior knowledge says that the theta can only take 3 values, which are 0.49, 0.52, and 0.55, right? So this is one way of saying that I believe that the coin is not that biased. It's closer to 0.5 as, let's say, compared to 0.8, right? Where 0.8 would be a biased coin and 0.5 will be a unbiased coin. So we'll assume that these are the 3 values that theta can take. And as I said, we assume a probability distribution over the parameter theta. Okay, so theta takes 3 values. So let's say our probability distribution over theta is given on the slide, which is 0.45, 0.39, and 0.16. Okay, so what we want to do is we want to compute the posterior in the context of Bayesian learning. Okay. Remember that in the fully Bayesian approach, we get a distribution over the parameter rather than a single value, as in the MLE approach. Okay, so let's see what this posterior looks like. So as I said before, posterior is nothing but directly proportional to likelihood times the prior. Okay, so if you remember, the likelihood function for this coin example is theta to the power of number of heads in the data times 1 minus theta to the power of number of tails in the data. Okay, so that's your likelihood function. And so when we have data set which says I have 6 heads out of 10, the posterior, which is P of theta given data for each of these 3 values, which will be directly proportional to theta to the power of number of heads, which is 6, times 1 minus theta to the power of number of heads, which is 4. Okay, multiplied by the prior. And the prior in this case for theta equals 0.49 was 0.45. For 0.52, the prior was 0.39. And for 0.55, the prior was 0.16. Okay. So now you have a posterior distribution over the 3 thetas, okay, and that will be a fully Bayesian approach. Similarly, if I have another data set where I have 53 heads out of 100, then I will get a posterior distribution over the 3 values of theta, which looks like that. except that now I'll raise 0.49 to the power of 53 because the data set has changed, right? And 1 minus 0.49 to the power of 47 because the data set has changed again, okay? Similarly for other values, okay? And I'll do the same calculation for data set 3. Again, what is going to change is the power, okay? While the prior will remain the same, okay? So let us see what the posterior looks like, right? So if you look at the posterior, then the posterior has the prior, which is just one value between 0 and 1, and other values which are also between 0 and 1, which are raised to some power, okay? So as you can see, as more and more data comes in, the likelihood term, which is that guy, because it's raised to, because these are nothing but probability terms raised to some power, and the power keeps on increasing as the data set size increases, that likelihood term will dominate the prior term, okay? So as more and more data comes in, you are going to believe the data more as compared to the prior, okay? However, if you only have, let's say, something like 10 examples, then you can see that the prior will impact what your results look like, okay? So let us now try to compare apples to apples. What I mean by that is, let us now try to compare MLE to the MAP estimate. So we saw that MAP was nothing but a generalization of the MLE in the context of Bayesian learning, okay? So if you remember, the way we compute MAP estimate is we look at the posterior, right? So let me erase all my drawings here. We will look at each one of these posteriors, right? So this is the posterior distribution, and MAP is nothing but a value of theta such that the posterior is maximized, okay? So if you look at this posterior distribution, you can go home and since you're already home in this case, but you can do these calculations at your own leisure, and you can figure out that actually 0.49, right, is the dominating solution. What I mean by that is this value is larger, right? So this value is larger than the other two values, okay? So that's why my MAP solution will be 0.49. Compare that to the MLE solution, right? So the MLE solution was 0.6, right? And actually, if you look at the MLE solution, and let's say there was a uniform distribution over theta rather than the prior that we have used, and as we saw, if theta is if prior which is a uniform distribution, then MLE will be equal to MAP, okay? So in that case, what we would have chosen is a value of theta which is closer to 0.6, which is nothing but 0.55, okay? However, because of the prior, right, and since the prior is not uniform, what is happening now is that the most likely estimate according to the prior, okay, so the most likely estimate according to the prior was 0.49 dominates, okay, because the probability of 0.49 was 0.45, okay? So that will be my MAP solution. When we get 53 heads out of 100, okay, we actually get a MAP solution which is closer to the MLE solution, and we get 520 heads out of 1000, we get a MAP solution which is actually exactly the same as the MLE solution, okay? So now you understand like what is happening here. What is happening here is that you have a prior, right, and the prior dominates when we don't have a large amount of data. But as the amount of data set increases, the likelihoods terms, right? So this is the term based on likelihood, and the other term is based on prior. The likelihood term starts dominating the prior terms, right? And the prior kind of vanishes. Okay? So now let's look at an example, the same point estimation example, but now what we're going to use is a continuous prior as compared to a discrete prior, right? So in the discrete prior case, we said that theta can only take 3 values. And in the continuous prior case, we are going to say that theta can take any value between 0 and 1. All we are going to do is put a distribution over the different values, or over these like infinite values of theta, right? Because theta is a real number between 0 and 1. So the likelihood function in this case is nothing but theta to the power of number of heads and 1 minus theta to the power of number of tails. So this likelihood function actually turns out to be a binomial function. Okay. So what we can do in practice is use a conjugate prior, right? So use a distribution p theta, which is a conjugate prior to the binomial function, which is nothing but the beta distribution. And what I mean by a conjugate prior is that when we multiply the likelihood function with the prior, we get the posterior distribution, which is in the same family of distributions as the prior. Okay, so an example will be, let's say the likelihood function belongs to distribution family 1. Okay, an example is a binomial distribution in this case, or even a Gaussian distribution for that matter. Let's say the likelihood function was Gaussian, and when I multiply that likelihood function with the prior, which belongs to, let's say, distribution family 2, the product of these two will also belong, which is nothing but the posterior, will also belong to distribution family 2, right? So the prior and the posterior are in the same family. So actually you can go on Wikipedia and you'll find like a nice list where if your likelihood function is of one distribution family, then what type of conjugate prior that you can use so that your prior and posterior are in the same family. Okay, so it turns out that for the binomial function, beta distribution is the conjugate prior. Okay, so if you had a multinomial likelihood function, then you would have used a Dirichlet distribution as your conjugate prior. Okay, so from your statistics 101 class, you can actually figure out that the beta PDF is directly proportional to theta to the power of alpha minus 1 times 1 minus theta to the power of beta minus 1, where alpha and beta are two parameters, which are two real numbers which are greater than 0. Okay, and this is how the beta function looks like for different values of alpha and beta. So when alpha and beta are equal to 1, okay, the beta function is nothing but the uniform distribution. Okay, when alpha is 2 and beta is 2, the peak of the beta distribution is at 0.5. Okay, so that peak is at 0.5. When the beta distribution has alpha equals 10 and beta equals 10, okay, the peak also appears again at 0.5, but as you can see that the rate of increase from 0 to 0.5 when alpha and beta are 10 is much larger as compared to the rate of increase when we have alpha and beta equals 2. Okay, so that's what happens. As you increase alpha and beta, this distribution will get kind of peaky, right? So when, let's say, alpha is equal to 100 and beta is equal to 100, this distribution will look something like this. Okay, pardon my drawings, but you get the idea, right? So it will be very, very peaky like that. Okay, so as I said, beta is a conjugate prior to the likelihood function. So when we multiply the likelihood function with the prior, what you get as output is also a beta distribution. Okay, so the posterior distribution is nothing but a beta distribution with alpha, which was the prior parameter, plus the number of heads, and the number of heads comes from the likelihood function. Okay, over there. And the second parameter of the beta distribution is beta plus number of tails, where the number of tails again comes from the likelihood function. Okay, so one way of looking at this is that what the prior distribution does is it adds extra heads and tails to your likelihood function. Okay, so when, let's say, alpha is equal to 1, right, the beta distribution looks like your original heads plus an extra added 1 to it. When beta is equal to 1 again, right? So let's say we were using beta distribution or the prior distribution, which looks like that. You're also adding like 1 to the tails. Okay, and when alpha and beta are equal to 10, right? What are you doing? You are actually adding 10 heads or hallucinating 10 heads and adding them to your data. Okay, so that's why sometimes the beta distribution is called, colloquially, right? I call it like this so-called hallucinating distribution, where you did your experiment somewhere else and you hallucinated that you got X number of heads and Y number of tails, right? And now you say that X is nothing but alpha and Y is nothing but beta in the original beta PDF. Okay, so that's what this is. So let's actually now compare how the MLE estimate, right, will look like as compared to the map estimate, right? So let's compare the map estimate with the MLE estimate, I should have said. So the MLE estimate, you know that it's going to be equal to number of heads divided by number of heads plus number of tails. Okay, the map estimate for this posterior will be nothing but alpha plus number of heads minus 1 divided by alpha plus number of heads plus beta plus number of tails minus 2. Okay, so all that has happened is that the numerator has increased by alpha minus 1 and the denominator has increased by alpha plus beta minus 2. Okay, so that's the difference between the MLE estimate and the map estimate, right? So you just have this extra hallucinated heads and tails, right, in your original data set. So is that clear, right? So same principle applies here in the sense that as the amount of data increases, right, as you can see in the map estimate at least, what will happen is that the number of heads term will dominate alpha. Okay, and once that starts dominating alpha, essentially the effect of alpha will start disappearing, right? So let's say the number of heads is now 5,000 and alpha is only 5, right? 5,000 plus 5 is closer to 5,000 as compared to 5. Okay, so the prior will disappear as the data increases. Okay, however, unlike the discrete prior case, right, there is a nice property that the beta distribution has because it's a smoother distribution, and the nice property is that we can actually give our prior distribution some strength, okay, depending on the values of alpha and beta. Okay. So as I said, when alpha and beta are large, the beta PDF is peaky, right? So our prior is stronger. When alpha and beta are small, our prior is not that peaky. So here are some of the terms in Bayesian learning that you should be aware of. The first term is that of marginal likelihood, which is the normalization constant in the posterior. Okay, so if you remember, we were trying to do theta given d, right? This is the posterior. This is nothing but equal to p of theta times p of d given theta. So likelihood and the so this is the likelihood and that's the prior divided by divided by p of d. Okay, where p of d is the marginal likelihood. Okay, so the marginal likelihood is equal to the integral over p of d comma theta, right, d theta, which is nothing but p of d given theta times p of theta d theta. The posterior predictive distribution, which is the distribution of generating a new data point, and this is important because this is the way you can sample when you have a model learned using the Bayesian learning approach rather than the MLE approach. So in the MLE approach, you are going to get a value of theta, right? And from that value, you can directly sample, right, and generate samples of heads and tails and so on. In the Bayesian context, what you have to do is you have to compute this so-called posterior predictive distribution, which is probability of generating a new point given the data set, right, and the prior distribution theta, okay, which is nothing but integral over of x given theta times the posterior, right? So this another way of looking at this is nothing but the expected value of x, which is a new data point, right, with respect to the posterior. Okay, the prior predictive distribution is the distribution of the new data point when you have no data set available, right? So when you have no data set available, all you have at your disposal is your prior, and so the way you're going to generate new data is by just sampling the prior. So in this case, this is nothing but the prior predictive distribution is the expected value of x again, right, with respect to the prior. Okay, and I guess you should be aware of two conjugate prior distributions which we will use extensively. The first conjugate prior distribution applies to binary variables, so when the variables can only take two values, either a 0 or a 1, and the conjugate prior in that case is the beta distribution, right? So in this case, the posterior will also be a beta distribution. When you have variables having more than two values, okay, you should use the multinomial distribution as your conjugate prior. Okay, and actually I've made a mistake in the slide. This should have been a Dirichlet distribution as your prior. Okay, so the posterior will also be in the will also be a Dirichlet distribution. Now let us generalize our Bayesian learning approach from the one parameter case to multiple parameters, namely a Bayesian network, under the assumption that the data is fully observed, right, or the FOD case. So FOD, if you remember, stands for fully observable data. Okay, the setup is quite simple, right? All you have to do in order to apply your result from the one parameter case to this multi-parameter case is make a very simple assumption. And the assumption is that we'll assume that each parameter has a separate prior, and the priors on the parameters are independent of each other. Okay, so let's say your Bayesian network has a set of parameters from theta 1 to theta m. Then the prior over all the parameters, which is represented by this set big theta, right, is equal to the product of the priors over the individual parameters, right? Why we can do that? We can do that because the priors, we are assuming that they are independent of each other. So once we make this assumption, what it means is that each parameter can be estimated independently, right? So now when we are looking at each parameter, we can look at each parameter in isolation and just apply the results of our one parameter case. Okay. For instance, let's say you are given a prior distribution over the parameter theta of x given u. Okay, so theta of x given u is a parameter which specifies p of, let's say, x equals x given an assignments to its parents, right? So this u is the bold u. So u are the parents of x, and small bold u denotes an assignment to the parents of x, right? And let's assume that x equals x means that x is equal to true. Okay, so let's say that this parameter theta of x given u is associated with a prior distribution, which is beta of alpha of x given u and beta of x given u. Okay? Given data, the posterior over theta of x given u. Now, if you remember or recall the results of our one parameter estimation case, if the prior is a beta distribution, then the posterior will also be a beta distribution. Okay, so in this case, the posterior is also a beta distribution, except that the beta distribution is now defined over alpha of x given u, which was the prior parameter, plus the counts from the data. So the relevant counts from the data. So the relevant counts for the parameter theta of x given u, right, for alpha are nothing but the number of times the assignment x comma u appears in the data set. Okay. Similarly, the counts that are relevant to the parameter beta of x given u. So beta of x given u, if you remember, these are nothing but tails, right? So tails is nothing but opposite of heads, in which in this case is going to be x bar instead of x. Okay, so that's why you have x bar. And the counts that are relevant in the data for beta of x given u are nothing but the counts over x bar comma u. So all you're going to do is count the number of times x bar comma u appears in the data set. So that's your posterior. From this posterior, we can easily compute its map estimate. The map estimate is nothing but the so-called alpha parameter of the beta minus 1 divided by the alpha parameter of the beta plus the beta parameter of the beta minus 2. Okay? And compare this to the compare the map estimate, I should say, to the MLE case. Okay, what's the difference? The difference is that in the MLE case, we only looked at the counts that are relevant to the parameter, right? And in the map case, we are so-called hallucinating, right? These extra alpha of x given u and beta of x given u, right? And adding them to these counts. Okay, so that's the only difference between the map estimate and the MLE estimate. So the bottom line is that Bayesian estimation in the context of Bayesian networks, under the assumption that the data is FOD, is very simple, right? All you have to do is just make a very simple assumption which says that the parameters are, or the priors on the parameters are independent of each other. And once you make that assumption, you can just apply the results, right, from the one parameter case to each one of these individual parameters, because they could be estimated separately. Okay, so that's what, easy peasy. Okay, so now comes the hard part, right? And the hard part is, how do I apply the Bayesian approach, okay, to parameter learning in Bayesian networks under the assumption that the data is partially observed. Okay, so if you remember our MLE learning, or MLE, I should say, in partially observed data, we know that the likelihood is no longer unimodal, right? So the likelihood is a multimodal function, and it can be highly complex. So we had to use algorithms such as gradient descent and the EM algorithm in order to solve this problem. Okay, so similar, since the likelihood is going to be multimodal, what will happen is that the posterior, even if we make assumptions that all the parameters are, or the parameter priors are independent of each other, the posterior will still be highly complex, right? Because the likelihood is complex, and it will also be multimodal. Okay, and the consequence of the fact that the posterior is complex and multimodal is that Bayesian inference, right, or Bayesian prediction, if you want to sample from sample a new data point, I should say, right, that would require a complex integration procedure, right? And this complex integration procedure will have no general analytic solution. Okay. However, the good news is that we can solve this problem of requiring complex integration, right? Or I should say we can circumvent the problem of requiring complex integration by using various approximate approaches. Okay, so one approximate approach that we can use in lieu of full Bayesian inference is to use map estimation. Okay, so if we use map estimation, all we have to do is, instead of finding parameters which maximize the likelihood of data in map estimation, we try to find parameters which maximize the posterior. Okay, so if you remember, the posterior is nothing but likelihood times the prior. Okay, so if I am maximizing the log of the posterior, I'm essentially maximizing the log of likelihood times the prior. Okay, so log of products is nothing but log sums, right? So you take the log of p of d given theta and add to it log of p of theta, which is the prior. Okay, so this function is nicely decomposable. Okay, and we can easily solve this optimization problem again using the EM algorithm or the gradient ascent algorithm. The only change, I should say, that we are going to make in the EM algorithm as well as the gradient ascent algorithm is that the objective function will now change to this, right? So your original likelihood, log likelihood function plus log of the prior, okay? And the algorithm will remain the same, right? So in the context of gradient ascent, for example, whenever I'm computing the gradients, right, I know how to compute the gradients of the likelihood. I'll add to it the gradients of the priors, right? And you're done. Okay. The second approach is to perform full Bayesian inference, but instead of using exact techniques, use approximate inference techniques such as sampling and variational inference. Okay. So in this case, the problem remains in that your optimization algorithm is no longer guaranteed, right, to converge to the so-called maximas, right, of the posterior, okay, because we are using approximate inference approaches. So now let me summarize what we just discussed for learning Bayesian networks using the Bayesian approach, right? The idea in Bayesian learning is to put a prior on the parameters. And the reason we are doing this is because we want to leverage prior as well as background knowledge that we may have about the domain. And the Bayesian approach is a nice formal approach for achieving this, okay, using prior knowledge along with data. So that's the idea, right? What we're doing is we are using the data to improve our prior knowledge, right? Combining the two and then making inferences using a so-called posterior distribution, which is nothing but the product of the likelihood and the prior. Okay. One nice aspect about this Bayesian approach is that when we don't have large number of examples, the prior dominates. And when we have large number of examples, or as the number of examples tend to infinity, the effect of the prior disappears. Okay, so we have a really nice approach which combines our prior knowledge with data. When you have large amount of data, let data do the work. When you have small amount of data, help the prior reduce the biases in the data. Okay. One important aspect of the Bayesian approach as compared to the maximum likelihood estimation approach is that it does not yield a single parameter value, right? So the fully Bayesian approach, what it does, it yields a probability distribution over the parameters. So if your parameter is a continuous quantity, which is going to be in our case, right, the parameter theta was nothing but probabilities, then it's going to yield a probability density over theta. Generally, full Bayesian inference will be harder than the maximum likelihood, than performing inference, I should say, on parameters estimated using the maximum likelihood estimation approach. Okay. However, if we use map estimates instead of the full Bayesian approach, our inference complexity in many cases will be the same as the MLE approach. Okay, but the map will have certain drawbacks, and one of the drawbacks is that it's only looking at the so-called mode of the posterior, and it's not looking at the so-called average case performance. Okay, so what I'm going to do is I'm going to end the lecture by making some jokes, right? So we saw two approaches. One was the frequentist approach, who used things like MLE, right, or the maximum likelihood estimate. And in a way, in some circles, the map estimate is also called as the frequentist approach, because you're given just like one possible value, right, for the parameter, and not a distribution over the parameter values. So in statistics, right, there is a big fight between the Bayesian approaches and the frequentist approaches, and sometimes the two communities come together, and I guess like 99% of the times, the two communities fight with each other, right? So every time the Bayesians say that, oh, we have a nice posterior distribution, and we have a nice distribution over the parameters rather than a single value, and a single value is never enough, the frequentists will come back and say that, oh, we have things like confidence measures on those parameters, right? So everything that you can do, we can do better, that kind of thing, right? But it's a healthy competition, and in general, at least in the context of the field of machine learning, right, there are more frequentists out there as compared to Bayesians. Okay, so let's end this lecture on a lighter note on how to fight with each other, right? So the first joke is saying that a Bayesian is a one who, vaguely expecting a horse and catching a glimpse of a donkey, strongly believes that he has seen a mule, right? So mule is a combination of horse and a donkey, right? And the Bayesian prior was saying that I see a horse, right, or I'm likely to see a horse. However, after seeing the donkey, it tried to combine the horse and the donkey and came up with the mule. What will the frequentist do? The frequentist will say that if I see a donkey, I have no prior, right? Which means that the next example has to be a donkey. It cannot be a combination of horse and donkey. The second joke is also interesting, right? So imagine that you're watching Game of Thrones or The Tudors on Netflix, right, or something like that. And let's say there was a Bayesian, right, and a frequentist, and both of them were to be executed. Okay, so there was a judge in the room, and the judge asked each one of them what were their last wishes. What did the Bayesian say? The Bayesian said that, oh, my prior is strong. So what he wants to do is he wants to give frequentist one more lecture. Okay, the judge granted the Bayesian's wish. Okay, and then turned to the frequentist and asked the frequentist, what is your last wish? What did the frequentist say? Frequentist said that I don't believe in priors. I believe in data, and I need a large amount of data. Right? So what is my request? The frequentist quickly responded and said he wished to hear the lecture again and again and again and again, forever and ever and ever. Okay? So this is how the frequentists saved Bayesians. Okay? So based on this joke, or I should say based on these two jokes, what I want you to estimate, right? So this is a homework question, and this is a fun homework. Estimate whether your professor is a Bayesian or a frequentist. Okay, So that concludes our discussion about Bayesian approaches for learning the parameters of the Bayesian network, right? Under the FOD case as well as the POD case. And next lecture, what we're going to do is we are going to switch gears and look at structure learning of Bayesian networks. So until now, we have only looked at parameter learning for Bayesian networks. Okay. Next lecture, we are going to look at structure learning algorithms for Bayesian network for both the POD as well as the FOD case.